Go back to thermodynamics. And we covered this first in Gen Chem 1. And the big discussion here, so thermo is heat, dynamics is change. We're really looking at endothermic versus exothermic. So a lot of this will seem like review to you. That's fine. That's fine. So we have a whole series of properties that we associate with these. And it's usually easier if I overview these just in terms of one of them. And then the other one is exactly opposite. So I'm going to go to exothermic. So exo, I always think of the heat's exiting. Heat goes out. I always think of burning wood in my fireplace. The reason I burn wood is not for the CO2 and it's not for the water. I don't want to make CO2, I don't want to make water, I want to make heat. And so heat is on the product side. So then endothermic heat goes into the system. It comes as a reactant. We'll look in terms of delta H. So exothermic is negative delta H, and we'll talk about what that is in just a little bit. So if I wanted to complete this, I could say this is heat in, heat's a reactant. I could say, I would just memorize one side.
And you'd be able to memorize the opposite.
And you got the other one because it's exactly.
The opposite.
Now the picture that we look at for exothermic, it's pretty similar to some of the reactions that we've seen in the past. The key there is the enthalpy, the H, or you can also think in terms of energy, is lower on the product side. We talked in terms of energy of activation. That would be this area there. So I could add a catalyst and lower that down. If I'm looking on this side then, it looks like this, where the reactants and the products have a higher enthalpy. So let's define some of my terms that I'm using in these things a lot. So H is enthalpy, which is a nice way of thinking about it. It's the energy trapped in the bond. Another name for that might be chemical energy. The energy stored in the bond. So when we burn gasoline to make our car go, the energy that we're releasing from that gasoline is what gives us the heat and the power to make our vehicle move. So when we see this delta, means change. So here it's going to be the products minus the reactants. Another term that we'll see is S, which is entropy. This is the amount of disorder.
You say change in H, delta H products minus reactants, you're referring to the heat in the product minus the heat in the reactant.
The enthalpy,
Okay, just
The
checking.
heat in it. So it's, don't think H is heat, it's enthalpy. So in science, we tend to use Q for heat.
Okay. Just an energy.
This is the chemical energy. That's a good way of thinking of it. And then E for energy. So now I'll have to look. If your book uses H for heat, then it's just another reason to hate it. But we'll do a lot with this reaction. The enthalpy is not too hard to measure because we can relate that to the heat and we can relate that on to the energy being transferred. Entropy is tough because the disorder is quite difficult to measure, to put a number on. We can look at something and say, hey, when it's a solid, everything's then kind of lined up in its place. When it's a liquid, they move around more often. And when it's a gas, they're really moving around randomly. That's a lot of disorder, but how do you put a number on that? So that's why we use our laws of thermodynamics. There's 3 laws on that. It's not in this chapter, so don't stress over writing them out. But it says that when we're at 0 energy, 0 Kelvin, 0 temperature, a pure crystal will have 0 disorder. So it just gives us a 0 point there so that we can start putting numbers with the entropy. And then entropy is just something you're going to have to look up every time. It's not something we can really then define here. Now we see another one that we'll see. And it's a G. We'll see that this chapter. And this is referred to as the Gibbs free energy. And so Gibbs free energy looks like that, delta H minus T delta S. So delta S, I didn't define that. What do you think it's going to be?
Entropy?
It's entropy of what? Well, it'll be the entropy of my products minus my reactants.
What does the T stand for?
What's the T stand for? Great question. What do we normally use the T for?
Time?
Temperature. And what units do we need? In Kelvin. The temperature has to be in Kelvin. Now, usually this is the delta G. They're simple for it, but you can take it in terms of G, it don't matter. So if I get a plus delta G and a minus delta G, they tell me 2 different things.